NEC Section 300.22 focuses on ensuring that conductors are protected from excessive current flow, which can cause damage or fires. This section mandates the use of overcurrent protection devices, such as circuit breakers and fuses, designed to interrupt current flow when it surpasses a predetermined safe level. The overcurrent protection device must be rated for the maximum current the conductor can safely carry. The conductor should be connected to the overcurrent protection device without any splices or taps, except as permitted by exceptions. NEC Section 300.22 provides exceptions in specific situations. Firstly, conductors of branch circuits rated 20 amps or less do not need overcurrent protection if they are fully enclosed within a raceway or cable. Secondly, overcurrent protection is not required for feeder conductors that supply a panel board or distribution panel from the service entrance. Thirdly, motor circuits rated 100 horsepower or less are exempt from overcurrent protection requirements at the motor itself. To ensure compliance with NEC Section 300.22, firstly, select overcurrent protection devices with appropriate amperage ratings. Secondly, provide a continuous pathway for current flow from the protected conductor to the overcurrent protection device. Thirdly, use listed and approved components. Non-compliance with overcurrent protection requirements can result in electrical fires, damage to electrical equipment, and potential injury or death. NEC Section 300.22 applies to all conductors, including line, neutral, and grounding conductors. The overcurrent protection device should be located as close as possible to the conductor it is protecting. In certain cases, multiple overcurrent protection devices might be necessary to provide adequate protection. The fundamental principle is to safeguard conductors from overcurrent situations, preventing overheating, insulation breakdown, and potential hazards. Overcurrent can arise from various sources including short circuits, ground faults, and overloads. A short circuit occurs when there is an unintended low resistance path between two conductors with different voltage potentials. This results in a very high current flow. A ground fault happens when a conductor comes into contact with a grounded surface, like a metal enclosure, creating an unintended path for current to return to the source. An overload occurs when a circuit is subjected to a current demand that exceeds its rated capacity. This can be due to too many devices operating on the same circuit simultaneously. Overcurrent protection devices respond to these conditions by interrupting the circuit. Fuses contain a metal element that melts and breaks the circuit when the current exceeds its rating. Circuit breakers use a bimetallic strip or electromagnetic mechanism to trip and open the circuit. The selection of the appropriate overcurrent protection device is critical. The ampacity of the conductor, which is its current carrying capacity, must be considered. The overcurrent protection device should have a rating that does not exceed the conductor's ampacity. NEC Table 310.15 provides ampacity values for various conductor types and sizes, taking into account factors like insulation temperature rating and installation conditions. It is important to note that the ampacity of a conductor can be affected by factors like ambient temperature and the number of conductors bundled together in a raceway. Correction and adjustment factors must be applied as specified in the NEC. For example, if a conductor is installed in a high-temperature environment, its ampacity is reduced. Similarly, when multiple current-carrying conductors are bundled together, their ampacity is reduced due to the increased heat generated. The location of the overcurrent protection device is also important. It should be placed at the point where the conductor receives its supply. This ensures that the entire conductor is protected. In some cases, it may be necessary to provide overcurrent protection at multiple points along a conductor run, especially if the conductor size is reduced. An example of this is a tap rule, which allows for smaller conductors to be tapped from larger conductors under certain conditions, provided that the smaller conductors are protected by overcurrent devices. The NEC also addresses specific requirements for overcurrent protection in different types of electrical systems, such as motor circuits, transformer circuits, and generator circuits. Motor circuits have special requirements due to the high inrush current that occurs when a motor starts. Overcurrent protection for motor circuits must be sized to accommodate this inrush current while still providing protection against overloads and short circuits. Transformer circuits also have unique requirements. Transformers can be damaged by overcurrents on either the primary or secondary side. Overcurrent protection devices must be selected to protect the transformer from these conditions. Generator circuits require overcurrent protection to prevent damage to the generator from overloads and short circuits. The overcurrent protection device must be coordinated with the generator's characteristics to ensure proper operation. It's essential to distinguish between overcurrent protection and ground fault protection. Overcurrent protection responds to overloads, short circuits, and ground faults, while ground fault protection is specifically designed to detect and interrupt ground faults. Ground fault protection is typically required for services and feeders rated 1000 amps or more. Ground fault protection devices, such as ground fault circuit interrupters (GFCIs), are designed to detect small imbalances in current flow between the ungrounded and grounded conductors. These imbalances indicate a ground fault. GFCIs are commonly used in residential and commercial applications to protect against electric shock hazards. They are required in areas where there is a high risk of exposure to moisture, such as bathrooms, kitchens, and outdoor locations. Another important aspect of overcurrent protection is coordination. Coordination refers to the selective tripping of overcurrent protection devices. The goal of coordination is to ensure that only the overcurrent device closest to the fault opens, minimizing the disruption to the electrical system. This is achieved by selecting overcurrent devices with different time current characteristics. The time current characteristic of an overcurrent device describes how quickly it will trip in response to different levels of overcurrent. Overcurrent devices with inverse time characteristics trip faster at higher levels of overcurrent. Coordination studies are often performed to ensure that overcurrent devices are properly coordinated. These studies involve analyzing the electrical system to determine the fault currents at various points and selecting overcurrent devices with appropriate time current characteristics. In summary, NEC Section 300.22 is a critical requirement for electrical safety. It mandates the use of overcurrent protection devices to protect conductors from overcurrent conditions. Compliance with this section requires careful consideration of conductor ampacity, overcurrent device ratings, location, and coordination. By adhering to these requirements, you can help to prevent electrical fires, equipment damage, and personal injury. It is important to consult the NEC and other relevant standards for specific requirements and guidance on overcurrent protection. The NEC is updated regularly to reflect changes in technology and industry practices. Staying up to date with the latest requirements is essential for electrical safety. Furthermore, it's crucial to understand the difference between different types of overcurrent protection devices. Fuses are single-use devices that must be replaced after they have interrupted a circuit. Circuit breakers, on the other hand, can be reset after they have tripped. There are different types of circuit breakers, including thermal magnetic breakers, which use a combination of thermal and magnetic mechanisms to trip, and electronic trip breakers, which use electronic circuitry to detect overcurrents. The selection of the appropriate type of overcurrent protection device depends on the specific application and the requirements of the electrical system. It's also important to consider the interrupting rating of the overcurrent protection device. The interrupting rating is the maximum fault current that the device can safely interrupt. The interrupting rating must be sufficient to handle the available fault current at the point of installation. If the interrupting rating is too low, the device may fail to interrupt the fault current, which can result in equipment damage or personal injury. Proper installation and maintenance of overcurrent protection devices are also essential for electrical safety. Overcurrent devices should be installed in accordance with the manufacturer's instructions and the requirements of the NEC. They should be inspected regularly to ensure that they are in good working condition. Any damaged or defective overcurrent devices should be replaced immediately. Furthermore, it is important to ensure that overcurrent devices are properly labeled. The labeling should clearly indicate the device's amperage rating and interrupting rating. This information is essential for selecting the correct replacement device and for troubleshooting electrical problems. In addition to the requirements of NEC Section 300.22, there may be other applicable requirements depending on the specific application. For example, the NEC contains specific requirements for overcurrent protection in hazardous locations, such as areas where flammable gases or vapors are present. These requirements are designed to prevent explosions and fires in these locations. It's important to consult the NEC and other relevant standards to ensure that all applicable requirements are met. Overcurrent protection is a complex and critical aspect of electrical safety. A thorough understanding of the requirements of NEC Section 300.22 and other relevant standards is essential for ensuring the safety of electrical systems. By following these requirements, you can help to prevent electrical fires, equipment damage, and personal injury. Remember to always consult with a qualified electrician or electrical engineer for assistance with overcurrent protection design and installation. They can provide expert guidance and ensure that your electrical system is safe and compliant with all applicable codes and standards. Electrical safety is a shared responsibility. By working together, we can create a safer environment for everyone.